it makes sense if heat makes an object swell, they get fluffier or less dense. And if cooling them makes them contract, then the density increases. So there's actually a link between thermal expansion and density. And we're going to see these two properties, which just seem like curious lab properties that occasionally gets annoying for our equipment and we design around it. It allows us to make thermometers and such. Actually has great implications for life on Earth itself and even eternal life, believe it or not. But let's start off simple. Let's look at the relationship between density and temperature. This kind of graph you must be able to deal with on a unit test. Simple explanations as to how it functions. So this is a graph of air density versus temperature. And it's important that you begin to understand how to read graphs. They make a lot of numerical calculations a lot easier, and there is a tremendous lack of understanding of graphing in the public. So right now I see a lot of misinformation and misinterpretation, perhaps deliberately so, of graphs showing the spread of COVID-19. So let's look at what this graph is showing us. On the horizontal axis, we have temperature from minus 30 degrees all the way to 40, or as I like to call it, Saskatoon. Notice I've avoided putting in anything to do cognitive dissonance, anything that's going to rattle your brain by presenting conflicting information simultaneously. I chose blue as a very low temperature color and red as the high, something you already expect. So I picked a color gradient to match your interpretation of color and temperature. Now let's look at the density one. And the density is on the vertical in kilograms per cubic meter. It could be grams per cubic centimeter, but kilograms per cubic meter is fine too. After all, most of the time we're not selling coal or water or oil in little tiny sugar cube sized chunks at a time. We tend to sell it in much bigger chunks. In fact, if you're dealing with water at Niagara Falls, you're talking cubic kilometers. So density in kilograms per cubic meter is totally fine. Now notice what I did with the color scheme here. Most of you are probably thinking I should have put the dark banding near the bottom, but I put it near the top. There's a reason why I did this. If I were to ask you to label this graph fluffy or dense, I want you to think which side of this graph is fluffy and which is dense. Now, while you've got a few seconds to think about this, let's look at reading this graph. So if I go ahead and go to 30 degrees Celsius, way over on the right, and I see where that dot is, and I track it back to my y-axis, I get 1.15 kilograms per cubic meter. I know it's not right on the line, but like seriously, get a life. We're not doing this thing for that kind of accuracy. All right. Now, we go to minus 20. And we follow over, and we get 1.4. So the density changed by this number. As the temperature came down, the density went up. Okay? So temperature going down, what's happening with the curve? It's moving up in height. Okay? I love doing this with a laser pointer in the cat. And then you just stop at a doorway, and the cat thinks the laser went under the door, and they'll stay there all night waiting for it to come out again. Like that, see? It just disappeared. Okay, now, the density went up. Does that mean the item became fluffier or more compact, more dense? Well, think about it. Cold things contract. So this is the higher density up here. And that's why I chose a darker color scheme here, because it represents more denseness. So if you were to label fluffy and dense now on this graph, where would you put these terms? You think you figured it out? This is where most people will put them. First chance I get in class for 30 years. 90% of students will immediately say It's less dense up here and more dense down there. Now, why do you think that happens? These numbers are showing that air is becoming more compact at lower temperatures. And as we go along here, the air begins to get fluffy at higher temperatures. And again, this is what we call cognitive dissonance. I think most people's brains are doing this. Up is where light, fluffy things go, like clouds and zeppelins, right? And down is where very heavy, dense things go. So your first reaction on seeing a density graph is to assume that the curve up here represents the fluffier substance, and down here we're seeing the denser substance. I would say that occurs for 90% of students over the years. So the correct labeling is this way. And I think when you see a density graph, the first thing you want to do is make sure in your head you are understanding what the graph is showing you in different directions. And by no means on a test, if I see you scrawl in the words dense or fluffy, am I going to think, stupid kid has to put the cloud and the block on the graph. No. If you don't understand what the graph is showing, then it's meaningless. After that point, anything you do has no meaning whatsoever because you didn't understand what you're doing. So by all means, label dense and fluffy on the graph when you see a graph like this on the unit test, because that will show me you were thinking and you listened to my stupid video. Okay? Now let's move on and look at two other substances. We're going to look at air again, and we're going to look at steel density. Now, first off, once again, we have a density in kilograms per cubic meter. And it would superficially seem that the densities are very similar to each other. They're both dropping in density, getting fluffier as they get warm. But these two graphs cannot be directly compared. First of all, look at the density range of air. And look at these numbers here. This is like anthill size density range. This is skyscraper. The range of density on iron is thousands of times higher than air. So these two aren't even on the same scale. What about horizontally? That's a 70-degree change in temperature. This one's changing 1,000 degrees. So these graphs cannot be read next to each other at all. They are totally, completely non-comparable in terms of their temperature ranges. This entire graph here would be like a kilometer below this one and squeezed into a spot smaller than this red dot. So you got to look at your scale ranges. You're going to do a lab in grade 12 physics with a pendulum and timing, and the scale range you'll slam right into that lab 3 years from now. Guaranteed. You'll hit it where you think you've seen something, but you didn't look at your scale. Now, I did a little math here. This density range here, 1.1 to 1.5, is a 24% change in density in only 70 degrees. Steel, this change here, even though numerically it was huge, that's a 500 kilograms per cubic meter difference in density. This one, that's like literally in a cubic meter, we're talking a couple of handfuls of popcorn are the difference in these two densities. But this one took 1,000 degrees. And a change in density in something like steel, it's already so dense, right, that a change in density is going to be a massive amount of weight. So it turns out this is really only showing a 7% change in that entire range. So when you spend some time and look at these graphs, it's not quite as obvious on the surface. You got to give yourself a few minutes to look those numbers over and try to decide what you're seeing before you start leaping to answers. So this is all I want you to see here. There are three materials. Top left is the density of air changing over temperature. The bottom left is the density of steel changing over temperature. And on the far right, methanol. It's a form of alcohol, not the kind you can drink unless you want to die horribly rather abruptly. All three of them are showing temperature drop. Now, the observant person might notice there's one weird thing here. Look at that. Temperature in Kelvin. What the heck is that? It's the same as Celsius. Just the 0 degrees is moved to the freezing of everything. Everything frozen. All the way down. Absolute zero. And what's the difference? If your house is 20 degrees Celsius right now, it's 293 Kelvin. When do you need to know Kelvin? Grade 11 chemistry. So this is in fact totally equivalent to these two. It's just been shoved over. That's all. Notice the densities aren't changing what we'd say linearly. This one here looks like a dead straight line, but you can sort of see steel. There's a itty bitty curve, and air, there's a little itty bitty curve, but it seems to be double the temperature and the density falls to half. Cut the temperature in half and the density doubles. That seems to be kind of the thing it's doing. So, why don't we try something humdrum? What do you think water looks like? I mean, how much could the density... You'd expect water to behave sort of like alcohol or air, right? It should be a nice, even change. Surprise!